In this section, we're going to talk about arc length. So recall that the radian measure theta of an angle is defined as the ratio of the arc length S of a circular arc to the radius r of the circle, or we can say that theta is equal to S over r. In a circle of radius r, the length of an arc S, subtended by an angle with measure theta, where theta is in radians. This is a really important part. If we're going to find arc length, we have to have theta in radians, is equal to S equals r times theta. Let's take a look at an example. Part A. Find the arc length along a circle of diameter 14 meters subtended by an angle of pi over 6. Round to the nearest tenth of a meter if necessary. All right, so what we know, let's see what we want to find, I should say. We want to find the arc length. So arc length formula is S equals R times theta. Do we know R? Well, r is the radius. We are given the diameter. So if the diameter is 14 meters, radius is half of that, so the radius is 7 meters. Okay, so in my formula for radius, I'm going to put 7 meters. Do I know theta? Theta is the angle measured in radians, and in this case, theta is given already in radians as pi over 6. So all I have to do is substitute that pi over 6 in there and multiply. 7 meters times pi over 6 would be 7 pi over 6. But this one says to round to the nearest tenth of a meter. So I'm going to put into my calculator 7 times pi, and then I'm going to divide that by 6. And that gets me approximately 3.7 meters. All right, let's try the next one. Find the arc length. So again, we're finding arc length. Find the arc length of a circle of radius 10 inches subtended by an angle of 215 degrees. Again, we're looking for S equals R times theta. And what do we know? We are, in this case, we were given the radius of 10 inches. So R is given as 10 inches. I always like to include those units because that's going to help me at the end to make sure my units are labeled. So the radius is 10 inches. And what is my theta? The angle is 215 degrees. Now this is where you have to be careful because in the definition, theta is measured in radians. So this is where I have to do a conversion. I'm going to say if theta is 215 degrees, that I'm going to multiply that by pi over 180 degrees and simplify to get the conversion from degrees to radians. Now I'm going to let you do that in your calculator. I got 43 pi over 36 when I reduced that fraction. I'm going to leave it in exact form, and if I'm going to round, that's not going to happen until the end. So I'm going to multiply this by 43 pi over 36 because that's my angle measure, and put it into my calculator. I get 37.5 approximately inches. So let's take a look at an application problem that involves arc length. The clock in my home office has a minute hand that is 4 inches long. How far does the tip of this hand move in 7 minutes? All right, so in this image, it does look like 7 minutes have gone by. Let me just draw in this clock. So assuming that maybe I started with the minute hand straight up at 6 o'clock, and it's going to end 7 minutes later, right? So that's 7 minutes have gone by. Okay, that's what we're looking for. So it says, how far does the tip of this hand move in 7 minutes? So 7 minutes have gone by, but we don't know the actual length of this piece. That's what we want to find. right? How far has it moved? And what we do know is that the length of this hand is 4 inches, right? Okay. So what we're looking to solve for is the arc length of that 7 minutes. So I want to find out S equals R times theta. So do we know R? R represents the radius, and that's the minute hand. So we're going to say that R is equal to 4 inches. All right, theta. So do we know what theta is in radians? We do not. We know what theta is in minutes, but we don't know what theta is in radians. But here's what we know. We know that a whole rotation around that clock in radians would be 2 pi. We are interested in 7 sixtieths of the clock, right? We're interested in 7 sixtieths of the clock. Where's the 60 come from? 60 minutes makes up a whole rotation of the clock. So 70 sixtieths of the whole clock is 2 pi. And so now we're going to multiply, because of typically means multiplication. We're looking for 7 minutes out of the whole 60 minutes of 2 pi. Okay, so that's going to get me, if I multiply here, that's 2 over 1, right? So 14 pi over 60, which reduces to what, 7 pi over 30? Does that sound right? And now we're in radians. I can write the word radian if I want, but remember I don't have to, because if theta doesn't have a unit mark, like a degree marker, then it has to be radians. Okay, now I'm ready to substitute into the formula. The arc length of that 7 minutes, what is the length of that 7 minutes, is going to be my radius of 4 inches multiplied by the angle, so 7 pi over 30. And if I multiply that, I'm going to get, it looks like I'm going to get 28 pi over 30. And if I grab a calculator and put into the calculator 28 times pi, all divided by 30, I get 2.932153143. This one doesn't tell me to do any sort of estimation, but if I were to say to someone, oh yeah, the space on my clock is 28 pi over 30 inches, they would not have a feel for what that is. So I'm going to round this and use a decimal of, say, 2.9, maybe I might even say 3 inches. It's about 2.9 inches in length. Now, one thing you might be thinking about here is, well, is there another way to do this? If this space up here represents 2.9 inches, I might be curious to know, like, what is the space all the way around the circle? Well, remember that represents circumference. Circumference is 2 pi r. That's what the formula is. So if I substitute in that radius of 4 inches, the whole clock is 8 pi inches. Well, what's 8 pi? 8 pi is 8 times 3.14, which is about 25.1 inches. So does it seem reasonable that you have a clock that all the way around is 25.1 inches, but just 7 of those minutes represent 2.9 inches? I feel like that makes sense. But one thing that you could have done, if you wanted, is you could find the whole circumference of the circle. So we know that the whole circumference, I'm going to move over here because I ran out of space. We know that the whole circumference of the circle is 25.1 inches. If we were only interested in 7 of those minutes, we could say that the arc length is 25.1 inches times only 7/60ths of that space. And if I do that multiplication, I sure hope that I end up with the same answer of 2.9, which I do. And you can double check that if you like. So that work in red was just a check. You don't have to find the whole circumference, but just in terms of trying to have it make a little bit more sense, I think that that helps a bit. Hope that helps. Now let's take a look at another application of arc length. San Francisco and Seattle have roughly the same longitude. The latitude of San Francisco is 37 degrees, 47 minutes north, and for Seattle, 47 degrees, 37 minutes north. Assume that the radius of the Earth is 3,960 miles. Find the distance between the two cities. Find the distance between the two cities. Well, let's first identify where are these cities. These two cities are both in North America, and we are given information about their latitude. The latitudes run horizontal, so I can see that horizontally we have some things labeled 20 degrees, 40 degrees, 60 degrees north. San Francisco is in North America at 37 degrees, around 37 degrees, so I'm going to make this dot large. That's San Francisco. And Seattle is going to be on that same longitude line, roughly, but with a latitude of 47 degrees, so maybe about right here. So we are interested in that arc length. Now, I drew it as an arc because if we're looking at the Earth as a round structure, then that distance is going to be an arc length. The radius of the Earth is 3,960 miles. So if I could connect these two cities to the center of the Earth, right, the distance between those two cities, we have to think about what is the angle between those two cities. And that brings us back to arc length. So we are interested in what is r times theta. We know that r has been given as 3,960 miles. All right, but what is theta? Theta is the difference between those two latitudes. So theta is going to be 47 degrees, 37 minutes, minus San Francisco, which is 37 degrees, 47 minutes. The problem with this setup is that I can't subtract 47 minutes from 37 minutes. So I need to borrow. And we're going to recall that 1 degree is 60 minutes. So if I take away 1 degree, then I can add 60 minutes. Okay, so this becomes 46 degrees, 97 minutes, minus 37 degrees, 47 minutes. So that subtraction gets me 9 degrees and 50 minutes. Okay, so now I know the angle between the two cities. I cannot use that number as theta, however, because the arc length formula, the theta has to be in radians. So what should I do? Well, I know how to convert degrees and minutes into degrees, and I know how to convert degrees to radians. So I got a couple more steps, but I can do it. So here's what I've got. I'm going to say theta is equal to 9 degrees plus 50 minutes, and I'm going to rewrite that 50 minutes as using the conversion of 1 degree is 60 minutes. All right, I'm going to multiply that. And if I multiply that, I get roughly looks like 9.833333 degrees. Okay, but that's not good enough. I need to convert the degrees to radians. So again, I'm going to use a conversion. I'm going to say that 9.833333 degrees times, let's see, I know that 180 degrees is equivalent to pi radians. So if I put that into my calculator, I get approximately, let's see here, I get approximately 0.1716 radians. Now, I'm writing these numbers, I'm terminating them sort of randomly here. What you should know is that when I'm using my calculator, I'm using all the exact computations in my calculator, and I'm only rounding at the very, very end. So even though I wrote 9.83 repeat in my calculator, I actually used the full, all those threes all the way out. And then when I multiplied that by pi over 180, let's see, I got, 9 plus 50 over 60, and then I times that by pi over 180, and I got 0.171624041. And so I wrote 0.1716. I'm going to write that up in my formula for theta, but what I'm actually putting in my calculator is that full thing that I just said. And so if I multiply 0.171624041 times 3,960, I get that the distance between San Francisco and Seattle is approximately 679.6 miles. So double check me on that. Make sure you've got your calculator in front of you. Maybe write a concluding sentence for this one. Because it got a little messy, the distance between San Francisco and Seattle is 679.6 miles. Now, if you put this in Google Maps, you might get a different set of mileage, but that's because Google Maps is excuse me, having you actually drive, and it may not be a straight shot. This number is the actual distance that, say, a bird could fly. So as the bird flies, that's what the distance would be. Hope that this helps, and we'll talk more about this stuff as we continue in trigonometry.